Let's get started. We have a new section, a last section to cover for the test. Not the last section in Calc 4, but the last section for the test. So what's it about? Well, we're going to do change in variable, which is...
So we aren't doing 15.5.
Which is? Which is the surface area. No, we're not going to do surface area. It'll take me 2 days to do this, and I think it's a natural finishing point. I know about surface area, even now I might change my mind. We're definitely not doing it this week. And that's as good as it's going to get. So, change in variable, you've done it in Calc 2. Remember U subs? That's change in variable. What does it do? Well, it allows you to take a single integral that may be quite hard to integrate or even impossible. And by a clever algebraic trick of changing the information to be in terms of a different variable, typically U, you can integrate that and get the answer you were looking for. So it's a classic strategy in math is, I've got a problem, I don't know how to solve it. So I'm going to change it into another problem that I do know how to solve. I find the answer to that new problem, and I use that answer in that new problem to figure out what the answer to my original one was. So it's a sneaky technique, and it's being used in Calc 2. Actually, it's used in Calc 2 in two different sections. There was a section called U sub that if you get me, you get them till you're bored stupid, because I think it's very important that you're good at U sub, so you do lots and lots of them. An example of that, if someone went and said to you that you'd like to integrate that, if you try and do that, it doesn't work. Integration by parts doesn't work. It's really not a very nice one. So we do a U sub, which would be in this case x squared. Let's make that 2x just to make the question even easier. If you did this as your U sub, it depends who you get, how you set this up. And what you eventually get is basically e to the u du. Although I can't integrate that, I can integrate this. And so there's my answer. But that's my answer in terms of u. And so when I return the u sub and use it in reverse, the antiderivative is that. So we've solved the problem. Now, without the trick of u subs, how to get from here to here would be, I can't say impossible. I guess you could guess it and you might get lucky. But you can imagine how complicated some U subs can be and how clever they are at changing things. So that's our goal. We're going to do that, but we're going to do it with double and triple integrals. So that's the change. Right? How do you do that? Well, before we get to step 3, which is how do you integrate using a change in variable technique, I have some skill building that we need to be getting used to first. So how do you find the determinant of a 2x2 and 3x3 matrix? Now this will test your skills. If any of you've done Math 250 linear algebra, you should be able to do this standing on your head. On the other hand, if you've never done that class, then you may not even have seen much of any of this. So here is a matrix for you. A matrix is really just a table of numbers. In this case, it's a 2x2 matrix. And it gets its name from the fact that it has 2 rows and 2 columns. So it's a 2x2 matrix. Now we are going to find a guy called the determinant of it. And the notation that we are going to use for the determinant looks like that. Do you know these two vertical lines that we're using here to signify that we're going to find the determinant of this matrix? Those two little lines are used in all sorts of things in math that are not necessarily connected. For instance, if I use those two little lines and a single number, is it not the absolute value? And the absolute value would be 7. If I use this same notation, but with a vector, what are you actually calculating here?
Good man.
Okay, and the magnitude here, I believe, is the square root of 14. But when you use it in the context of this, it's called a determinant. Does anybody actually know how do you get the determinant of a 2 by 2 matrix?
You just multiply them diagonally.
Yes. So there are two diagonals. This diagonal going this way is called the major diagonal. That's its name. And the way you get a determinant is major diagonal take away the other diagonal, which is called the minor diagonal. So major take away minor. In this case, -1. Have you noticed that a determinant can be a negative number? The absolute value of something is never a negative number. And this fella, would you agree that although that's the same symbol, aren't these three totally different things? And it's just the fact that there are only so many brackets and lines that we have in math that a lot of symbols get double duty. In fact, since I'm at that, do you recognize these funny little guys? Aren't they the greater than and less than symbol? But when you use them in matrices, aren't they nothing to do with greater than and less than? Aren't they just the symbols for the special brackets that vectors get? So are we all comfortable with the fact you could have the same symbol being used for totally different reasons? Because we've only got so many symbols in the world, in mathematics at least, that almost everything gets used in 2 or 3 places for 2 or 3 totally different reasons. So back to this guy. Are you okay about a 2 by 2? Do a couple more just for practice then. 5, -1, -2, 1. 3, 3, 1, 7. If you're going to do this one, it's major diagonal 5 times 1, take away minor diagonal. That's 5, 2, 5 take away 2 gets you 3. Major diagonal, take away minor diagonal, 21, take away 3, I believe you get 18. So if I gave you a 2 by 2 matrix, would you be comfortable with major diagonal, take away minor diagonal? Now, let's suppose I wanted the determinant of this matrix, where instead of numbers, we have variables. Do you think that's going to make a big difference to the process?
No.
No.
Exactly. Right, okay, it might take a little bit more work. If you do the major diagonal, take away the minor diagonal, you don't get anything particularly interesting. No, occasionally, not this particular question, but can you imagine that sometimes these terms might combine or cancel out or simplify in some way? And that, if it's doable, you should do that. Okay. Is it possible for the determinant of a 2 by 2 matrix to be 0?
Yes, it is.
It's bad news if that ever happens, and it's not going to happen in any of our questions. And if you think it's happened, you've made a mistake. Right? So just put that down there. You ain't getting 0. Now, could you get positive or negative things? Darn sure you could. Didn't we get a negative one today? And we've got 18 as well. So yeah, a 2 by 2 matrix could be positive, negative, or 0. An expression like this is more likely to what we've got. Well, that was the easy one. That's how you do a 2 by 2. You don't get as many questions, but we do need to do a 3 by 3. You don't need to answer this question in specifics, but in general, have you seen the determinant of a 3 by 3 matrix? How many of you have actually seen that process?
Me.
Was it in Math 250 or just somewhere else?
250.
250. Has anybody else done 250 then apart from her?
I'm in it right now.
Have you got to the point where you've done the 3 by 3 or not?
Yes, we have.
Right, so there's 2 of you are going to be happy and the others are going to be miserable. Would you agree that the determinant of a 3 by 3 matrix is just clunky?
Yes, it only gets worse with size.
Right, the bigger the worse. We only do 3 by 3, but theoretically 4 by 4 and so on. So, to get a 3 by 3 matrix, there is a formula which I don't use because it's a downright ugly formula. Is that how you learned to do it, or did you do it by geometry? By pictures? Can you remember?
We did, I forget the exact name for it, but we would go along a row or column.
Oh God, no, don't. Okay, we are definitely not doing it the way you did in 250, so I am winding that back. All of you are going to have a hard time. So this is the geometry way of doing it. You start with the first row. The first guy is 5. You cover up that row and that column. There we go. Do you see a little 2 by 2 matrix there?
Oh, so it's the same way as in.
Okay. So it's 5 times the determinant of that 2 by 2. So you take a 3 by 3 and you reduce it into combinations of 2 by 2. So that's the first one, 5. The next number is a 2. And it's negative whatever that number is. It's just, that's the row. And if you cover up the row and the column that is in, do you see you're left with a -1, 2, -2, 4 guy? And then you got the third one, which is back to 7. So it's 5 times this, take away 2 times this, plus 7 times that guy. Now that's basically visual, right? That's what I mean, geometry. It's a visual technique. The 250 people, have you seen that technique?
That's
Yes.
what we used.
Okay, so you're back to being the way you're used to it. I thought you were going to do row echelon reduced matrix version, which is definitely not the way to go. Not for these. Right, so don't we know how to do that? We've just done them a minute ago, right? These are 2 by 2 matrices. So here goes. This bunch here gets you 5 times major 12, take away -2. Subtract 2 times major diagonal -4, subtract -4. Plus 7 times major diagonal -1, subtract -6. Let me slow down that again. 5, yeah. 12, take away 2, check. Subtract 2, yeah. -4, take away -4, yep. 7, yeah. -1, take away -6. So what do we get? We get 5 times 10, take away 2 times, 0, plus 7 times 5.
So how come we're taking away the 2 and adding the 7?
It's
So
part
it's-
of the pattern. It's really just you do it. You do it because you're told to do it. There is if you go deeply into matrices, you'll find that calculating the determinant is based on operations done on various rows and columns. And if you do it as a generic version, you find out that that negative appears as part of the process. All you're going to have to do is say, yep, it's negative. By the way, changing tack here, do you know if it's a 4x4? You use the first row, and let's pretend the numbers are 1, 2, 3, and 4. It's 1 times a 3x3, right? Then you take away the second one, 3x3. Then you add the third one, 3x3, and then you take away the fourth one. So it has this plus minus pattern forever. You don't notice it until you've done 3 or more. If you did 10, it would be first, take away second, plus third, take away fourth. And a 10 by 10 would turn into 9 by 9s, which would turn into 8 by 8s. Oh God, forget it. Computers, right? That's what we'd use. Right, in this case, I got 50, take away nothing, add 35. Hopefully I can count right. There's your answer. Right, for the 2 and 250s amongst you, that's pretty much the general way that you would set it out. Yes, no, maybe.
Indeed.
Indeed. So for you, that's, oh, I'm 250 again. Right, do another one. 1, 3, -2, 1, 2, 4, 0, 3, -7, right? Start with the first row. So it's going to be 1 times something, take away 3 times something, plus -2 times something. Each of these somethings is a 2 by 2 matrix. So for the first one, number 1, it's this guy. So it's a 2, 4, 3, -7. For the middle one, it's 1, 4, 0, -7. And for the last one, it's 1, 2, 0, 3. So it's going to be 1 times. If you get quick at these, you do the major take away minor in your head. So what's that? -14 take away 12 is -26. Then you go -3 times, -7 take away nothing, it's -7. And then you go 3 take away nothing is 3. So I get -26, add 21, take away 6, 32, -11, I believe. Are we comfortable about how to get determinants of 3 by 3 matrices? Do you want to see another one, or do you get the gist of the process? I mean, you're in charge here. You tell me. I don't know. Yeah, I feel okay. I'll get used to it. I'm sure if I do a couple, they'll come to me. Or I'm not sure quite yet what he's doing. Where are you? I have to
Can
go
we do
back.
a couple more?
Sure. I'll do one number and one with variables. So here's one with numbers. -2, 5, 0, 3, 1, 7, 2, -1, 1. So it all hinges on the first row. So I'm going to take the first number, which is -2, and multiply it by a 2 by 2 matrix. Take away the second number times a 2 by 2 matrix. Add the third number and a 2 by 2 matrix. Right. Back to the first number, -2. If you cover up the row and the column, you will be left with the 2 by 2 matrix that you're going to be using. In this case, it's that matrix there, 1, 7, -1, 1. If you go to the middle one, I can't really cover it up so well, but here we go. If you go to the middle one, can you see that the 2 by 2 is a 3, 7, and a 2, 1. And if you cover up the last one, you get a 3, 1, 2, -1. If you get really lucky, as I did, can't we just put +0 for this one? Because it really doesn't matter what that is, it's going to get down to 0. Right, this fella here then is -2. To get the answer to this, it's major take away minor. So it's 1 times 1, take away -7. So 1 times 1, take away those two. And the middle one is -5, 3 take away 14. And so I get -2 times 8, subtract 5 times -11, plus some zeros, -16, plus 55, there's a 0. I'm not risking that today. -16, add 55. I am looking at positive 39. What's the best way to describe this? It's quite mechanical, isn't it? I mean, it's not a formula like plug and jug, but isn't it? Once you've done one 3 by 3, haven't you done every single one in the universe? The only thing that's different is the numbers, right? Basically, it's very mechanical. So let's do one with variables in it. Let's suppose this is U, V, 2U, W, 3W, minus U, U squared. Now, the process is going to be the same. The difference here is that there are variables involved, not numbers. So that's the key, this fella. So it's U times some 2 by 2, take away the second one, and add the third one. So it's U, V. Now, if you want to get the first one, that's that guy. You're going to deal with a 3, a W, a U, and a U squared. If you want to do the middle one, the top row is WW, and the row underneath is -U squared. And if we want to do the last one, the top row is a W and a 3, and a -U and a U. Are you comfortable about how this became that? Okay. Now, major diagonal 3 times U squared, subtract minor is that guy. Take away the, it's my dogs. Major diagonal is U squared W, take away -U W. And the last one is 2U, and it is UW, take away -3U. So let's see what we get. I get 3u squared, take away u squared w. This times this is negative u squared vw. This is positive, but then another negative, so negative uvw. This is 2u squared w. And those very crunched up guys is plus 3u, so 6u squared. If you scan across these, you may get some combining. That guy and that guy are the same.
Wouldn't it be
The three.
3u cubed, not
Which one?
3u
Here?
squared?
No,
Okay.
at the beginning.
No, at the beginning.
And this is good as a square, right? I did this one right. Yes, I did. This is a square. Okay, these two combine, but you're right. That guy and that guy got what? One of these. And that guy at the end is a plus. Okay, that is a 3 by 3.
Wouldn't it be negative 6u squared?
Let's check
'Cause
it
it's-
out. It's a take away a negative 3u. Let's check that it is. So we've got uw, take away a negative 3u, which means a plus, and 2u times a plus is a plus.
Oh, okay.
But, you know, I don't mind people asking me because, hey, I made a mistake there and you wouldn't know if you didn't tell me. Okay, so that's a 3 by 3. So that's taking care of the first topic for today, I hope. How do you find the determinant of a 2 by 2 matrix? So now we're going to find a guy called the Jacobian. So I want you to imagine that our change in variables are those two. In other words, x is going to be returned into u squared plus v squared, and y is going to be turned into u squared minus v squared. Oops.
In your background filter, it looked like you were standing on the chair in the background.
I was closing the door, so we went. So what is a Jacobian? Now, going back a bit, this is how substitution is going to work in this world. You know how you normally say u is a function of x? That would be the way you do it in Calc 2. Here, x is going to be a function of u and v, and y is going to be a function of u and v. Do you see? It's kind of turned on its head, but you have done that before. Can you remember in Calc 2 having to do x subs? Where you did a change in variable, it was called trig substitution, and you would do it for things like x over the square root of x squared minus 1, right? You remember that weird, by sheer coincidence, my Calc 2 class just finished that yesterday, right? So it is possible. So what is a Jacobian? It's written like this. So that's how you write it down. It's like a multi-dimensional version of things like that, right? So what this is saying is that we're going to do a partial derivative. It's called the Jacobian. This is its a notation. And it's a 2 by 2 determinant. And it's the partial derivative of x with respect to u, partial derivative of x with respect to v. So the top row has x's in it. The next row, du, dv. So a Jacobian is made up of the determinant of a 2 by 2 matrix. That's why I spent some time today doing determinants of 2 by 2. So what would the Jacobian of a three-dimensional changing variable look like? think pattern, think extending pattern. What do you think the top row would look like for a 3x3 Jacobian?
Delta X, delta U, delta X, delta V, and delta X, delta W.
Does that make sense? Can you see the pattern being continued? Now, the second row would have Y's in it with respect to U, with respect to V, and with respect to W. And then the last one would have Z's with respect to U, with respect to V, and with respect to W. And the reason why we need these Jacobians is that when we eventually come to tomorrow, probably, the change in variable, this is going to be an integral, important part of that process. So let's show you some Jacobians, which are changing variables, essentially. Do you remember this particular guy? Who is this guy if it's 2D?
Polar coordinates?
Polar. Now, when you did polar, didn't you have a funny RD theta? And I just said, look, trust me, you need that R, right? It's part of the question, right? That R is the Jacobian. So let's prove it to you. Let's find the Jacobian dxy by dr theta. Well, it should be the partial derivative of x with respect to r, the partial derivative of x with respect to theta, the partial derivative of y with respect to r, and the partial derivative of y with respect to theta. Are we comfortable about this Jacobian where all these pieces are coming from, right? X and y, r and theta. Now, if you differentiate x with respect to r, you get cosine theta. If you do x with respect to theta, you get negative r sine theta. If you do y with respect to r, you get sine theta. And if you do y with respect to theta, you get r cosine theta. Are you comfortable with those four pieces? Agreed? Now, major diagonal, cosine theta, r cosine theta. Subtract minor diagonal, minus r sine theta times sine theta. This gets you r cos squared theta. Two negatives become a plus, r sine squared theta. Pull out r as a common factor. And boom, they are. So how does that happen? This is how it happens. Do you know the guy that we typically call dA, right? dx dy, right? He is the Jacobian dr d theta. So this fella here is where that comes from. So it's not magic, is it? That r is there for a very specific reason. The Jacobian is how you transfer an xy coordinate derivative, or an xy differential, I should say, into an r theta differential. which really means that we have got a massive power here. Can I make up my own versions of x's and y's? Can I say x was r squared and y was sine theta? Because I wanted to, right? If I decided to use those particular substitutions, wouldn't I be able to find the Jacobian of it? And that would generate a weird guy here. But I could change my variables from x and y into whatever I decided. Now, the guys that we found that are the most useful, and that's why we tackled them, are polar, cylindrical, and spherical. Have you noticed that those three had their own little niche market? We did questions on each of them. Do you know those three could have been done as a really, really big section called change in variable? And we would have taken your original question and done a substitution that generates polar, or a substitution that generates cylindrical, or a substitution that generates spherical. Now, I wish I'm hoping I still have it, because it's a pain, because I never memorize these things. Well, of course, I don't have it, but I can find it. Has someone got the notes handy? I want to do spherical. So, whoa, that's noisy. I'm going to put you on mute. Go hunting for spherical, because I'm going to hunt for it. And if you get it first, tell me.
I got it.
Okay, go for it. What's x?
Rho sine phi cosine theta.
Okay, next one.
Y is rho sine phi sine theta.
And z?
Z is rho cosine phi.
Now, these were what we call, oh God, stop being annoying. My screen was going all weird on me there. This is essentially a change in variable, isn't it? It's a treble change in variable. It's x, y, and z being turned into versions of rho, phi, and theta, right? Can you remember, because hopefully, because I can't, can you remember what dv, which is what dx, dy, dz turned into?
Can we see your paper?
Oh, sorry. I've tried to close too many windows. I lost track of it, right? Okay. What is dv, right? The dx, dy, dz guy. Do you have that handy, Lindsay?
No, it's
Rho
phi squared.
sine phi d rho d phi d theta.
Right. Can you say that? Is it phi squared? Rho squared.
Yeah.
Right.
Sine
Then-
phi.
Gotcha. D rho, d phi, d theta. In particular, remember that magic that's there because it's there. Just trust me. Right. The rho squared sine phi. Agreed? You're looking puzzled. Is that correct? Lindsay, have you locked out on me? Maybe that's not a puzzled look. It's good, right? I'm moving on. It looks like Lindsay's picture just froze. Okay, so let's figure this fella out. I'm going to find this Jacobian, and he's going to be this fella. So that's where this fella came from. He is the Jacobian. He's the extra little bit you get when you do a change in variable. So I'm going to have to push this one. dx by d rho, dx by d phi, dx by d theta. dy by d rho, dy by d phi, dy by d theta, dz by d rho, dz by d phi, dz by d theta. You happy about the 3 by 3? Massively ugly guy. Okay, if you differentiate this with respect to rho, you get sine phi cosine theta. If you differentiate it with respect to phi, you get rho cosine phi cosine theta. And if you differentiate it with respect to theta, I should have planned ahead, shouldn't I? With respect to theta, you are going to get negative rho sine phi cosine theta over here. Move on to this fella. You'll get a sine. If you do it with the phi, you get a rho cosine sine. And if you do it to, wait a minute. Let me just check this one with theta. You do. I rubbed it out and I shouldn't have bothered. It was right all the time. Okay, and if you do the y fella with respect to theta, you'll get a rho, a sine of phi, cosine of theta. I am rushing this and it is not a good idea. This fella gets you cosine phi. This guy gets you negative rho sine of phi, and this guy gets you a 0 at the end. So you're going to have this first fella, which is this term, times the 2 by 2 matrix that looks like this. Then you're going to take away the middle one. I mean, this looks weird, but it's really just simply the same rule, but with lots of ugly pieces in it. So I'm taking this one. So we get and then you get this fella. And you cover this guy up, you're going to get this fella here, this fella here, this fella here, and this fella here. And now I'm going to do a cheat because we have 2 minutes and I don't want to do it. Can you imagine me doing minor takeaway, major taking away minor times this, major takeaway minors times this, major takeaway minor gives you this. It will be carnage. It will be massively big. But this will cancel, this will cancel. All sorts of things will cancel. And almost like magic, that will be left behind. And remember, they're going to be taking out common factors and sine square theta plus cos square theta becoming 1, right? That's going to happen as well. You're just going to have to trust me on this. That's where that came from. Now, what that means is that we have on our control a very powerful way of taking any double, that'll be this guy, or triple, that'll be this guy, integral, and change its variable so that we can integrate any double or triple integral we like by just choosing an appropriate use up. Or guess I shouldn't call them new subs anymore, an appropriate changing variable. That means, G, that you can create a new coordinate system. And it's not going to be spherical or cylindrical. It's going to be the Coulomb-Bally coordinate system. And if you create a really useful one, you'll probably get to name it. Unfortunately, I doubt very much that there are any other ones out there that are useful. They're all going to be useful for one-off situations, right? You have to create one for a special circumstance, but it's probably not going to work in a bigger world. I think cylindrical and spherical polar are probably it. Oh, and Cartesian, right? Has anybody got a thought in their brain about a changing variable coordinate system that you think might be very useful? Because I'd like to steal it if you do.
Probably make your career as a mathematician if you come up with one, right?
You will get major buccal kudos if you come up with one. The problem is really brighter people than me, because everybody's brighter than I am. I've just been doing it longer. That's the only difference. Haven't found one yet. Now, the one thing about mathematics that I think we've all learned is never say never. There may be one hidden out there, but it might be a fourth dimensional one, right? Where you're doing a quadruple integral. So I'm trying to imagine how you might be able to adapt, say, spherical to a fourth dimensional world. That one might be useful because space-time is a coordinate system that they use in cosmology, don't they? In planets and the universe. You know, fourth dimensions makes more sense to them than three because of Einstein's special theory of relativity. So maybe there's one out there that we haven't figured out that might be very useful. Maybe just a special version of it that is very helpful when you model black holes, perhaps. That would be interesting if they come across it. But that is us for today. When I see you tomorrow, we are going to use these fellas, Jacobians, to do changing variables of double and triple integrals.